Good morning, everyone. Interactive Weekly Math Reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. This session will provide the count of passport points, and the code will be posted on the chat towards the end of the session. So now, at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information we will be sharing. Without further ado, I'll pass it on to the presenter so that we may begin.
Good morning, everyone, and thank you again for joining us for our Happy Math Hour. We're almost there, guys, or it's almost half of the semester's gone by. So today we are going to be covering the review for our second exam, okay? So again, for those of you who are here for Math 1324, you'll find the link on the chat. Just go ahead and click on it, and you'll be transferred to the other room to go over Math 1324. Okay, so the rest of you who are here for pre-cal 1, let's go ahead and get started. So again, we are reviewing, and the sessions that the sections that we're going to be going over is 2.1 through 2.6. So your second exam is chapter 2. Okay, all of chapter 2. All right, so let's look at some problems. Okay, so to start reviewing, let's look at this rational function. Okay, this is a function that's with a fraction. Okay, and when looking at these functions, we always want to make sure that our denominator is never equal to 0. And if it is, it's going to have a restriction on our domain. So here, that's one of the first questions that it's asking us on this question is state the domain of the function. Yes. So again, we want to make sure that our denominator never becomes 0. So if we don't see it, what we want to do is we want to make sure that we solve or set the denominator equal to 0 and then solve for x. Yes? So in here, my denominator here is x plus 3, and I'm going to solve for x. And by solving for x, it tells me that if I ever use -3 for x, I'm going to get a 0 on the denominator, right? So that means that I can use any number except for this -3, okay? It's going to be excluded in our domain. So which answer would be on our multiple choice here, okay? It would be the last one, right? It's all real numbers of x except for when x is equal to -3, okay? So again, when dealing with rational functions, we never want our denominator to be ever equal to 0, and if we do, that it will be a restriction on our domain. Okay, so let's answer the rest of the information. We need to identify the intercepts, both the x and the y, for this problem. So again, to review, to find x-intercepts, we're going to set y equals to 0 and then solve for x. So again, y is replaced by the f of x. So we have 0 is equal to 1 over x plus 3. I'm going to multiply by x plus 3 on both sides. And when I do that, I get a false statement, right? 0 is not equal to 1. So then that means that there aren't any x-intercepts. When my statement is false, that means that x does not exist or the x-intercepts don't exist. Okay. Now for the y-intercepts, it's just the opposite. I'll set x equal to 0 and then solve for y. So again, we are everywhere we see x, we're going to plug in the 0. And when we do this, we are going to simplify and get that the y-intercept is 1/3. So when x is equal to 0, y is equal to 1/3. So that is my y-intercept. Now, to find any vertical and horizontal asymptotes, we've actually already discovered our vertical asymptote. When we were solving for the restriction on our domain, um, we saw that we couldn't use a value, right? So these are the steps to find the vertical asymptotes. We need to factor both the numerator and denominator completely, okay? And then we set the denominator equal to 0 and then solve for the variable again, which we did already in the previous step, right? So we had this question. Now we need to factor both the numerator and denominator. Um, and I see that my numerator is already factored out. It's already in simplest form. Same with the denominator. So that takes me to my second step where I set the denominator equal to 0. And again, we had done this work already. So this x equals -3 that gave me a restriction on my domain is now my vertical asymptote. Okay, so at x equals -3, I have an imaginary vertical line that my graph does not cross or touch. Okay? So again, the way we indicate the asymptotes on our graph are these dashed lines or these little dots, right? Um, so let's answer the second part, the horizontal asymptote. So for horizontal asymptote, we have several cases. Okay, so we have these 1, 2, 3 scenarios that will determine if we have a horizontal asymptote. So the first case, or the number 1, says if the degree of the numerator is smaller than the degree of the denominator, then there is a horizontal asymptote at y equals 0. Okay. The second case, we have a ratio. It says that if the degree of the numerator is equal to the degree of the denominator, then we have a horizontal asymptote of this ratio, which we get by uh, dividing the leading coefficient of the numerator by the leading coefficient of the denominator. Okay? And then the third case is if the degree of the numerator is larger than the degree of the denominator, then there exists no horizontal asymptote. But the third one does give us to where it won't have a horizontal asymptote, but it's going to have a slant asymptote, okay? And that's if the degree of the numerator is one more than the degree of the denominator, okay? So let's look at our example. If we see here on my function, the degree of the numerator is 0. Now again, let me see, let me pull out my pen. I can write the numerator like this, x to the 0 power, because anything to the 0 power is 1. Here, the bottom one, the degree is 1, right? So here we can see that the degree of the numerator is smaller than the degree of the denominator because the degree of the numerator is 0. The degree of the denominator is 1. So when we have this case, we're going to have a horizontal asymptote at y equals 0. Okay, so then again, we represent our horizontal asymptote as a dashed line, or in this case, dotted line. Okay, so again, the blue line is my horizontal asymptote. My pink line, I guess, fuchsia line, here is my vertical asymptote at x equals -3. And now we can continue building our graph. Okay, so to build our graph, we can go ahead and put what we have. We have no x-intercepts. We have a y-intercept at 1/3. We have a vertical asymptote at -3. We have a horizontal asymptote at y equals 0. Okay, so when I put all this information here, okay, to get a better sense of our graph, what we can do is always plot additional points. And what I like to do is I always like to put values that are left and right of my asymptotes. Yes, so in this one, I'm gonna pick -2, which is to the right of my asymptote, to see what the behavior of my graph is. Okay, so when I plug in -2 um, for x, my y value is 1. Okay, and then I also picked the value for 2, the +2. Okay, and then somewhere over here next to my y-intercept from 0, I picked 2. Okay, so when I plugged in 2 to my function, I get my y value of 1/5. So I can go ahead and pick some additional points. Again, I picked points to the right of my vertical asymptote. Now let's pick some points to the left of my vertical asymptote. So here I picked -4. So when x is equal to -4, I get y equals -1. And I also picked x equals -5. So when x is equal to -5, I get y is equal to -1/2. So let's go ahead and plot these points. And again, these are my points here. And then what we try to do is connect them in a smooth line, right? If we're doing this by hand, it would smooth line like this and like this. So here we see it, that the computer did it for us. Okay, on the right of the vertical asymptote, this line gets very, very close to this asymptote. Again, my graph will never cross or touch that line. And then it comes down to my horizontal asymptote. I have a horizontal asymptote here at y equals 0 where my line does not cross or touch. The same thing here on the left hand side, right? My graph is coming from -infinity and never crossed the y equals 0. And then it's getting very close to my vertical asymptote and never crosses it or touches. This is my graph, yes? All right, so let's look at another example again, answering all of the questions that lead us to our graph. So we have this function 3x plus 2 over x plus 3. Let's state the domain of the function. Again, the domain of the function is if we have any restriction on our domain, we're going to account for them, right? So again, for our first step, we notice that it's a fraction. Again, we can never have a 0 on our denominator. That's the equation on the bottom. So let's go ahead and set x plus 3 equal to 0. And again, it becomes the same value. Give me 1 second. Okay, there we go. So it's x plus 3. Again, we're going to solve for x. We subtract 3 on both sides, and we discovered that x is equal to -3. So again, just like the problem before, it's the same value. We can use all values for x except for -3. So what would be our answer here on our multiple choice? It's going to be the second one. All real numbers of x except for when x is equal to -3. Okay. All right, so then we move to our intercepts. Again, let's find our x-intercept. To find our x-intercept, we're set y equals to 0. So to solve for x, we're going to multiply both sides by x plus 3. And when we do that, on the left side, we get 0. The x plus 3 divided by x plus 3 becomes 1. And 1 times 3x plus 2 is just the 3x plus 2. Now we can solve by subtracting 2 on both sides. This is going to give me -2 is equal to 3x. Then I'm going to divide by 3 on both sides. And when I do that, I find my x-intercept. This function here has an x-intercept at x equals -2/3. Now let's go ahead and solve for our y-intercept. To find our y-intercept, we're going to set x equal to 0. So everywhere I see x, I'm going to plug in the 0. And then I'm simplifying. 3 times 0 is 0. 0 plus 2 would be 2. And 0 plus 3 is 3. So I have a y-intercept here at, there's a little mistake here. There should be y here. Okay, that's supposed to be y. Okay, so our y-intercept, y is equal to 2/3. Okay. So let's find our vertical asymptote. Again, we already solved our vertical asymptote when we were trying to find domain of the function. Okay, again, we solved for the vertical asymptote by setting the denominator equal to 0, and we discovered that x equals -3. This is our vertical asymptote, our equation of vertical asymptote. Okay. All right, now let's find, again, we label this as a dashed line, vertical line, here at -3. Let's go ahead now and solve for our horizontal asymptote. So let's look at this problem again. Okay, so here the numerator, the degree of the numerator is the one with the highest exponent value, right? The variable with the highest exponent. Here I only have one x, and that means that I have a 1 here. On the bottom one, I only have one x, so that means that I have a 1 here. So here in this problem, the degree of the numerator is 1, the degree of the denominator is 1. So these are both equal to each other. And when we have this situation where the degree of the numerator is equal to the degree of the denominator, we're going to have a ratio for our horizontal asymptote. The ratio of the horizontal asymptote is given by the leading coefficient of the numerator divided by the leading coefficient of the denominator. So the leading coefficient of my numerator is 3. The leading coefficient of my denominator is 1. So 3 divided by 1 is 3. So my horizontal asymptote is at y equals 3. And again, we represent this by a horizontal line, dashed line, or dotted line. Okay. All right, so this is what we have so far. We have our x-intercept, y-intercept, vertical asymptote, horizontal asymptote, so we can start our graphing process. Okay, so let's go ahead and build what we have. Okay, again, the one in blue is my horizontal asymptote, the one in pink is my vertical asymptote, and here my green dot is my y-intercept at 2/3. The black one is my x-intercept at -2/3. Okay, so let's get some additional points. And again, I want to get points to the left and right of my asymptote and of my points. So again, values on the right of my vertical asymptote, I pick again -2 and 2. Okay, when I plug in x for -2, I get a y value of -4. When I plug in an x value for 2, I get a y value of 8/5. Okay, so now let's look at some values to the right of my vertical asymptote. And again, I pick the same values, -4 and -5. So when x is equal to -4, I get a y value of 10. When x equals -5, I get a y value of 13/2. Yes, so let's go ahead and plot these points. Again, I plotted these points both on the right and left of my vertical asymptote, and then I let the computer do the work, right? The computer did this nice smooth curve graph that represents my function. Okay. All right, let's do one more. Consider the following. H of x is equal to x squared minus 9. So let's find the domain of the function. So this one, it looks like it's straightforward. Um, Again, there's only the variable x, so that means that x could never be 0, right? So here, our answer would be all real numbers except for x equals 0, okay? So that's what we're going to exclude from our domain or our restriction, all right? So let's go ahead and solve for our x and y intercepts. To find my x-intercept, again, I set y equal to 0, multiplied by x on both sides. I'm going to get 0 is equal to x squared minus 9. Okay, I'm going to add 9 on both sides and then take the square root of both sides. And I find that x is equal to plus or minus 3, right? So I have two x-intercepts for this problem. I have an x-intercept at 3 and one at -3, right? So let's find our y-intercepts. To find our y-intercepts, we set x equal to 0. So everywhere we see x, we're going to plug in 0. So here, okay, we can't do this because we have a 0 on the bottom, right? So this is going to be, does not exist. So that means that this guy has no horizontal asymptotes. But then again, we could have done this with our cases, right? Uh, well, actually, I'm getting ahead of myself. So this one has no um, y-intercept, excuse me. So now let's look at our vertical asymptote. Again, our vertical asymptote, we always want to factor both the numerator and denominator. And the reason why we want to do this step before is because if there are any factors that we can simplify out, um, they become gaps in our graph. They become holes in our graph. Okay, so those holes are not necessarily asymptotes. So that's why we always want to factor out both our numerator and denominator, because sometimes we can simplify things out that will um, eliminate possibly one of our asymptotes. Okay, and again, that asymptote wouldn't be an asymptote; it would just be a gap in the graph, which is a hole. All right, so in this case, I factored both of them out just to see if anything simplifies, but nothing simplifies, yes? So again, on this problem, my only vertical asymptote is my restriction or my domain, which is x equals to 0, okay? Now again, for the horizontal asymptote, which is what I was going to get ahead of myself, okay? If I see here, the degree of my numerator is 2, if I can write. So here's 2, and on the degree of my denominator is 1. In this case, my degree of my numerator is larger than the degree of my denominator, so that means that I'm not going to have a horizontal asymptote, okay? So there won't be a horizontal asymptote, but in this case, there will be a slant asymptote, okay? So if the degree of the numerator is 1 more than the degree of the denominator, the answer is yes. So then that means we have a slant asymptote, okay? So the way I like to find my slant asymptote, or my equation of my slant asymptote, is I just do, I divide this polynomial, right? This function, right? So again, I'm going to use synthetic division to do my division. Um, Here, again, we have to keep in mind that we're only using the coefficients of the um, polynomial on the top. So we have a squared, right? So we have to have three values. We have to have the square, the single x, and the constant. So if we see here, we're missing the single x. So I represent that by 0. Again, the coefficient of the x squared is the 1, and the constant is a -9. Okay, so I'm going to divide by 0. So again, I bring down my 1. 0 times 1 is 0. 0 plus 0 is 0. 0 times 0 is 0. And -9 plus 0 is -9. So this problem here identifies that my quotient here, okay, the negative is just my remainder, but uh, the only equation that is left over is this part, 1 and no constant, right? So the this polynomial is just x. So this would be the equation of my slant asymptote. The equation of my slant asymptote would be y equals x. Okay. Now, if I would have, let me go back to this. If I would have had a a constant here, my equation would have been x plus the constant. Yes. So in this case, it's just this y equals x slant line. All right, so let's see what we have. We have our x-intercepts. We have y-intercept that name right. I must have missed it. Vertical asymptote at x equals 0. Again, we have no horizontal asymptote, but we have a slant asymptote. Let's go ahead and get some additional plots. Um, so again, this is my slant line. Okay. This is my x-intercept, y-intercept. I think this is incorrect, the y-intercept. Um, and then let's get some additional points. So get additional points. Again, I'm choosing 2, 4, -2, and -4. Okay, so when I plug in 2 to my function, when x equals 2, y equals to -5 halves. When x equals 4, y equals 7 fourths. When x equals -2, y equals -5 halves. when x equals -4, y equals 7/4. Okay, so let's go ahead and plot those points here. Okay, and then we're going to let the computer do our work because again, we need to zoom out here. So we see here, we do not have a y-intercept. Again, this was a little typo here. So there's no y-intercept here. Um, we just have our x-intercept at -3 and at +3, and we have our slant line. Okay. All right. So let's go to another topic where we have write the quadratic function in standard form and then identify the vertices, axes of symmetry. Okay, so let's go ahead and do this. So to convert this quadratic, which is in general form, ax squared plus bx plus c, we want to do something that's called completing the square. Okay, so the way we do it is we first are going to isolate just the two terms that have the x, which is what we did here, right? We have 2x squared plus 8x, and then I close the parentheses plus 7. Okay, the next thing that I'm going to do is I always want my a to complete the square. I need to have a as equal to 1. Okay, so I'm going to factor out a 2 from the first two terms. So when I do this, I have 2 is equal to x squared plus 4x. Okay, so again, to find out or to make this into a perfect square, I'm going to use um, this notation. Okay, this is my a and this is my b. I'm going to take um, half of b and then I'm going to square it. Okay, and when I do that, okay, that's going to give me my perfect square constant term. Okay, so when I did this, when I did 4 divided by 2 and squared it, 4 divided by 2 is 2 and 2 squared is 4. This is telling me that if this constant, the c part, is a 4, this would be a perfect square. Now, I want it to be 4, but I can't just add 4 because I feel like it. But what if I added this? 4 minus 4. Well, what I'm truly adding is 0, right? I'm not adding anything. So if I'm adding 0, I'm not changing the problem whatsoever. So now what I like to tell my students is that we're going to do a little bit of math manipulation. I'm going to borrow the positive 4. So I'm going to close my parentheses. I'm going to move my parentheses to the positive 4. So I can only just have this, the x squared plus 4x plus 4. But if I'm taking the negative 4 outside of the parentheses, I got to give back what I had taken away originally from the what was inside my parentheses, this 2. So I have to give back this 2 to this negative 4. So 2 times negative 4 is negative 8. So now that negative 4 is outside my parentheses, okay? And here, again, this process that I did here of completing the square, I made this x squared plus 4x plus 4 into a perfect square. I made it into the x plus 2 times x plus 2. Now, if you're wondering, well, how did I know that? How did I know that this is equal to this, right? So all I have to do is look at first my b value. The sign of my b value is positive, so my two terms that I'm being multiplied have to be positive. Now here, I don't have it here, but the number that got squared before I got the 4 was a 2. 4 divided by 2 squared was a 4. So that I know that the 2 is what's making my perfect square. So that's where I get the 2 from. So again, here the outside gets simplified. The negative 8 plus 7 just becomes a negative 1. And I can rewrite this as a perfect square. This is the same thing as 2 times x plus 2 squared minus 1. And again, I converted my original function, which was in general form, into what's called standard form, okay, or vertex form. And we love this problem. We love this function in this notation because it tells us exactly what the vertex is. This graph got shifted 2 units to the left, 1 unit down. So my vertex is at -2, -1. The axis of symmetry is always the x value of the vertex. Again, it's this vertical line is my axis of symmetry because it has y-axis symmetry. So our equation of our axis of symmetry is x equals -2. Okay. All right. Ms. Chuka, would you like to take over?
Sure, thank you, Ruben.
Oh,
All right,
wonderful.
so the next part is finding the zeros of this polynomial function. And so there's different ways that we can solve these functions. And so we'll go ahead and start with, let's go ahead and continue here. So one of the things that we can do is we can set the function equal to 0 since we're trying to find the zeros. And then we're going to go ahead and factor out, if you notice, the polynomial has t, at least a t in common. So we can factor out a t squared. And if we factor out a t squared, and this x here should be a t, by the way. But if we factor out a t squared, we would get t squared minus t minus 30. So if you were to multiply this t squared back into the parentheses, we would end up with the same thing here. So if we're doing these problems and you can factor out a variable, then that is probably going to simplify the polynomial for you. Now what we have left in the parentheses, we can try to factor that as well. If we're not able to factor it, then we can use the quadratic formula. But here we can, so we would end up with t minus 6 and t plus 5. Notice that the 30 is 6 times 5. I need it to be a 1, so that is why I chose the 6 and the 5. Other factors of 30 could have been 3 and 10, 15 and 2, but those will not give us this -1 that we need. Now that we have factored, we can set each factor equal to 0. And so for the first one, we end up with t equals 0, since the square root of t on both sides, square root of 0 is 0. For the second one, if we add 6 on both sides, we get t equals 6. And then if we subtract 5, we get t equals -5. Another thing that it's asking us to do is determine the multiplicity. And basically the multiplicity is asking how many times does the 0 appear. And so for the t squared, if we take the square root, we get a plus or minus 0. And so essentially that is 2 of the zeros here. So in reality, we have t equals 0, and it appears twice. So we say that it has an even multiplicity. So at that point, the graph is going to touch and turn. For t equals 6, it only appears one time. So that has an odd multiplicity. So that's going to cross, if we graph it, the graph is going to cross through that point. And then the last one is t equals -5. And that also appears one time. So that means that your graph is going to cross at that point as well. So if we were to kind of graph this, you can see here that at t equals 6, the graph is crossing. At t equals 0, it touches and it turns. And then at t equals -5, it crosses. It didn't ask to graph it, but I wanted to show you the graphs just so we can see and make that connection. So just to review the end behavior, I like to use these 4 graphs. If you remember these 4 graphs, then you can always remember the end behavior. So here it says that determine the left-hand and right-hand behavior of the graph. So to determine the behavior, we're looking at the degree of the polynomial and the coefficient. If the degree is odd, then it's going to behave like one of these 2 graphs here with the odd power. If the leading coefficient is positive, then it's going to have the same behavior as f of x equals x cubed. So our answer for this would be that the graph rises to the right and it falls to the left. For multiplicity, I also like to focus on just 2 graphs that we have been working with all semester. So if you notice here, if the graph repeats itself, if we were to find the zeros of x squared, we would get x equals 0 and x equals 0. And at x equals 0, it touches and turns. For x cubed, if we were to solve for x, we would get x equals 0, x equals 0, and x equals 0. So that would have an odd multiplicity, so it's going to cross through that point. Another theorem that is helpful is the rational zero test, and this helps us to find the possible zeros. So if we're trying to find the zeros, this is going to allow us to have a smaller list to check. The way it works is we're going to look at the constant. You want to find the factors of the constant. So the factors of 9 in this case are 1, 3, and 9. But we're also going to use the negatives because we can make combinations to get this negative 9. Now, the other thing we're looking at is the factors of the leading coefficient. In this case, the leading coefficient is 1. So the factors is going to be 1. So what we can do is we're going to look at the factors of 9, which are plus and minus 1, plus and minus 3, plus and minus 9. And the factors of 1 are plus and minus 1. So if we divide, we get 1 divided by 1 is 1. 3 divided by 1 is 3. And 9 divided by 1 is 9. So if we list them out, we would have our answers, our possible zeros, are negative 9, negative 3, negative 1, 1, 3, and 9. So in WebAssign, we have to enter it in this way since they don't have the plus or minus symbol. So why is that important? Well, if we were to extend our question to actually say find the rational zeros, then we can take this list here and we can test them to see if they're zeros. I always like to start with the 1 and then go from there. So if I try 1, then we have synthetic division. So the coefficients are 1, 1, negative 9, negative 9. So if I drop my 1, 1 times 1 is 1, plus 1 is 2. 2 times 1 is 2, plus negative 9 is negative 7. So we end up with negative 16. Since my remainder is not 0, that tells me that x equals 1 is not a 0. So we can go to the list and try a different number. So we're going to try negative 1. So we do the same thing. Drop the 1 times negative 1 is negative 1, plus 1 is 0. 0 plus 0 times negative 1 is 0. Add the negative 9. Negative 9 times negative 1 is positive 9. And so now we can see that we have remainder of 0. So that is good news for us because that tells us that x equals negative 1 is a 0. But why is that even more important is that now we can use the quotient. So let me get the quotient here, x squared minus 9. And we can set that quotient equal to 0. Solve for x, take the square root, and so we get that x is plus or minus 3. So we're able to find all the zeros. Remember, the degree is 3. That means we have 3 zeros. In this example, our zeros are negative 1, negative 3, and positive 3. The factors, since we'll use them later, are going to be x plus 1, x plus 3, x minus 3. So let's try a different one here. It says list all the possible zeros and then list the real zeros and the multiplicity and determine the maximum number of turning points, and then lastly graph the function. So again, if you notice here, we can factor out an x squared, and that would make things a lot easier to solve for the real zeros. But I'm going to go ahead and do it the longer way, just so that we can get some practice. But again, let me get my pencil out here. Give me a second. So earlier I mentioned that if you want to find the zeros, we're always setting that equal to 0. But then I also said if you can factor out any of the variables, then you want to do that because it will simplify things, right? So if here we get x squared, if I can factor this, that would be x times x, and then 6 would be 3 and 2. My signs have to be different since I have a negative. And so if you notice here, by working it out this way, I can find my zeros probably a little bit quicker. Now the thing is, if you feel more comfortable using synthetic division, then you can just use synthetic division. But if you feel comfortable factoring, then this would be one way to finding your zeros. Okay, so but let's continue with the synthetic division. So here I'm going to use synthetic division. So I have a 1, a -1, a -6. There's no x, so I use 0, and there's no constant, so I use 0. So here my possible zeros would be, my constant is 0, so anything divided by 0 divided by any number is going to be 0. So we have one possible 0, which is 0. So if I use that and I do synthetic division, then I end up with this here. So since I had x4, now I'm going to go with x cubed minus x squared minus 6x. And so again, notice that this is cubic, so that means that I cannot use quadratic formula or factor yet. I mean, we could factor out an x, but I'm going to go ahead and use synthetic division anyways. I would repeat the same process with x cubed is 1, negative x squared has a -1 coefficient, -6 and 0. There's no constant, so my only possible option is 0. And if I use synthetic division, now I can break it down to x squared minus x minus 6. So now this part is quadratic. So for that part, we can factor if we're able to. But if you're not sure about factoring, then we can use the quadratic formula. Okay, so let's see what I use. So I use the quadratic formula just to give us a different method of solving. So here's your quadratic formula. If you plug in everything, then you'll notice that you still get the same zeros. Okay, so again, there's different options for us to factor or to find these zeros. So again, our possible zeros were 0. Then we had our zeros were 0, 0, -2, and 3. The 0 appears twice, so it has an even multiplicity. And so that's going to touch and turn, and then the other two will cross. So determine the number of turning points. So for that one, we take your degree and we subtract 1. So our degree is 4, minus 1 is going to be 3. And then we're ready to graph. So first, I like plotting my zeros, -2, 0, and 3. So -2, 0, and 3. Then I like to, at the end behavior, since this is a 4, that means that the graph rises to the right and it rises to the left. So I just kind of put my arrows pointing. I know that at this 0, x equals 3, it's going to cross. So I extend it through. And at x equals -2, it's also going to cross. And now to finish this, I would need to have extra points. I can pick points in between my zeros and figure out what they are. So here I pick the -1. When I plug in -1 into my function, then I end up with a -4. So I plot it here. And then for 1, if I plug in my points, I end up with -6. And then for 2, I end up with a -16. So I know that at this point 0, it's going to touch and turn. So then I can sketch my graph. It's going to come down here. It's going to touch, turn, and then it's going to come back up. And so that would be your graph. Of course, a prettier version with the computer. With the computer will look like this. But at least if we do it by hand, then we can identify it if it's a multiple choice question, for example. So then we have find the polynomial of the real coefficients that have the given information. So here they want a polynomial of degree 4. They give you 3 zeros and a solution point. Since you have a degree 4, that means that you should know what the 4 zeros are, but they only give me 3. So the missing 0 is going to be the conjugate of I, which would be negative I. So my 4 zeros are negative 4, 1, I, and negative I. We want to put the factors, so we get x plus 4, x minus 1, x minus I, x plus I. We don't know the coefficient, so I'm just going to write it as an, and then I list my factors. So you can multiply these out in any order that you prefer. I prefer to do the imaginary numbers first. So I'm going to multiply x times x squared. X times I is ix. Negative I times x is negative ix. And negative I times I is negative I squared. Now here we know that I squared is going to be, well, first we just rewrote it, and then I get x squared. The ix and the negative ix is 0. And so now for I squared, I know that that's a negative 1. So I can replace it with negative 1. If I simplify, we get x squared plus 1. So now I just need to multiply these three factors together. So x times x squared is x cubed. X times 1 is x. Negative 1 times x squared is negative x squared. And negative 1 times 1 is negative 1. I'm going to keep multiplying. X times x cubed is x to the 4th. X times x is x squared. X times negative x squared is negative x cubed. X times negative 1 is negative x. 4 times x cubed is 4x cubed. 4 times x is 4x. 4 times negative x squared is negative 4x squared. And then finally, 4 times negative 1 is negative 4. So then we want to find any common terms. So let's gather our common terms. So we have x to the 4th. I have a negative x cubed and a 4x cubed. So that would be 3x cubed. Then I have an x squared. A negative 4x squared would be negative 3x squared. And then our x's is negative x, and 4x will be 3x. And then my constant is negative 4. So now we just need to figure out what an is. So they also give us a solution point, and they tell us that f of 0 is equal to negative 8. So in this solution point, we know that x is 0 and y is negative 8. So we plug in that information. F of x is negative 8. And anywhere that I see an x, I'm going to replace it with the 0. And if I simplify, I end up with negative 8 equals an times negative 4. Divide by negative 4, so we get 2. If I plug that in, for an, we get this, and then last, we just multiply it out. So distribute the 2 into the parentheses, and then this would be our remaining answer. So that is how we would find the solution, the polynomial function. Now the last one, use the given 0. So this is my given 0 to find all the zeros of the function. So one way you can do it is use synthetic division. So here's x cubed is 1, x squared is negative 12, x has a coefficient of 52, and then we have negative 80. Since it's a 0 at the end, I better have remainder 0. So I bring down the 1. 1 times 4 is 4. 2i times 1 is 2i. Negative 12 plus 4 is negative 8. And then the 2i stays there. So then we multiply again. So we have 4 times negative 8 is negative 32. 4 times 2i is 8i. 2i times negative 8 is negative 16i. 2i times 2i is 4i squared. So if we simplify this, let me go back. 8i minus 16i is negative 8i. And then we're going to simplify to, sorry, let me go back one more time. And then I squared is negative 1 times 4. And that's how we get negative 4. And so now if we add all this together, negative 32 and negative 4 is negative 36. And so we end up with 16 minus 8i. So then we multiply again, 4 times 16, 64. 4 times negative 8, negative 32i, 2i times 16, positive 32i, and 2i times negative 8i is negative 16i squared. The 32i's will cancel. I squared is negative 1 plus times negative 16 would be a positive 16. And so we end up with 64 plus 16, which is 80. Negative 80 gives me 0. So I knew that should happen because they told me that's a 9. Well, if I get the quotient, I get x squared minus 8 plus 2ix, and then plus 16 minus 8i. So what I can do is, since 4 plus 2i is a 0, I also know that 4 minus 2i is a 0. So I'm going to use synthetic division again. So I have 1, negative 8 plus 2i, and 16 minus 8i. So I drop the 1. 4 times 1 is 4. Negative 2i times 1 is negative 2i. So notice that your i's cancel. Negative 8 plus 4 is negative 4. And then negative 4 times 4 is negative 16. And negative or positive 8i, so we get 0. So now our quotient is x minus 4. Set that equal to 0. And we get our last 0 of x equals 4. So all the zeros are x equals 0. So actually it should be x equals 4, right? So this should be a 4. Let me erase that. So this should be x equals 4 from this number. And then you have your complex number that was given, and then your conjugate. The degree is 3, so you should have 3 zeros, which we do. And so so that is how to find the rest of the zeros given imaginary solution. Most of you will have your test next week. So we wish you the best. And I think that's all that we have today. I'll pass it over.
Okay, thank you so much, Ms. Chuka, for that wonderful presentation. At this time, I would like to also invite all the attendees to our Tejano Virtual Event presentation today at 1 p.m. Today we will have the Writing Center and Succeed with CSD, the Center for Students with Disabilities. For next week, for the Happy Math Hour, we will have Math 1314 Exponential and Logarithmic Functions and Math 1324 Systems of Equations. For the Student Success presentation, the libraries will present with Blake Kizmasara. So thank you very much. If you have any questions, please address them right now. If not, you all have a wonderful weekend. Thank you.